Recording. Recording is in progress. Okay, okay. Wait a moment. Okay, so today we will talk about the convolution. And firstly, we need to know how to generate some simple singulars. And there are two basic singular functions, and they are step function and the impulse function. And for the step function, you can see that if n is greater than or equal to 0, the function value is 1. So it's like a step, right? For the impulse function, you can see there is only one value when n equals 0, and there is no any value around the other parts. So we call this impulse function, delta of n. And there is a simple operation that is reflection over y-axis. And if we define the function, which is the mu of minus n, it means this is a reflected, sorry. Okay. And the mu of minus n is the reflection, reflected step function over y-axis. You can see for the step function mu of n, there is no value for the negative part, but for the mu of minus n, there is no value for the positive part. So you can see for the impulse function, the delta of minus n equals delta of n. That's because we only have values at n equals 0. So let's move on. And the second operation is the shift. If you want to shift the step function mu of n and to the right by 3 minutes, you can define your single function as mu of n minus 3. If you want to shift your step function to the right by 8 units, you can define it as mu of n minus 8. This is the same for the impulse function. You can see for this figure, I just shift the impulse function to the right by 3 units. For this figure, I just shift the impulse function to the left by 2 units. Okay. So they are the two basic operation. One is the reflection and the second is shift. Okay. Next, by using these two operations, we can define our simple singulars. For example, if we want to define the W of n, and which is the mu of n minus 3 minus mu of n minus 8, you can see this equation according to this according to these two figures, the subtraction of these two singulars, you can see this part are cancel out. So the remaining part is focusing on this part. So you can see the mu of n minus 3 minus mu of n minus 8 is defined like this way. If we just define the W of n with the length of 20 samples, we can see the rest part are filled with element 0. And even if we can define the W of n as this equation, but I think most convenient way is define it as the summation of the impulse function, summation of the shifted impulse function like this way. Here you can see, since we only have the function has values over 3, 4, 5, 6, 7, so we can define the singular as the summation of shifted function, shifted impulse functions, like this way. Okay, and in this paper, in the paper of lab 2, the input singulars is x of n, and it is defined as this way, and you can see, in addition to this figure, and the new part is this Miller's impulse function at when n equals 17. So now we know that this x of n is the input singular. Okay, move on. Suppose that we have a linear time invariant system, and h of n is the impulse response, x is the input singulars, and y is the output singulars, and here x is the input singular, and h is the impulse response function. Both of them have the length of 20 samples, 20 units. Okay, 20 samples. And we can, and according to the singular and system, the output of n should be the convolution of x of n and h of n. So it's defined as this equation, and it's the sum from, oh, sorry, wait a minute. Let's make some small modification. Wait a minute. Wait a minute. This is this equation, and we can see, it's the sum from k equals minus infinity to infinity, x of n minus k, h of k, and actually, we can write it in the other form, like this. Actually, I'm more comfortable with this form, and it's the sum. It's a sum from k equals minus infinity to infinity, h of n minus k, x of k. And the difference between these two equations is that I just change the order of these two symbols. Yeah, you may notice that. By and then we can write it this n minus k as this way, minus k minus n. You can see they are the same. According to this equation, according to this final equation, we can find 3 steps of convolution, which is first, to generate the output of n, we should firstly find the singular. We should find the singulars of h of minus k minus n, and the second step is do the production of h and x, and the second and the third step is doing the summation over k. Yeah. For the first step, you may notice that this equation h of minus k minus n, actually it has the basic operations that is introduced before, and the shift, the reflection operation, and the shift operation. You can see actually we generate this h of minus k minus n. You firstly need to reflect the h of you need firstly reflect the h of k over y-axis to get the h of minus k, and then you just shift this reflected h to the right by n units. Yeah, so it becomes this way. This is how we generate the h of minus k minus n. Okay, next. Then I will show you the animation of convolution. Firstly, since this singular is the input singular, and we just want to generate the y of 0, since so firstly we need to generate the h of minus m minus 0, so it becomes like this way. So actually this is equal to h of minus m, so it's just the reflection of h of m. Okay, like this way. And then you do the production of these two singulars, and then you sum up all values over k, and you can see the final results are 0, since there is for the h function, there is only one value at when k equals 0, and for this part, for k equals 0, x of 0 is 0. So do the production and the summation, the final answer is 0. And okay, next is to generate y of 1, and since to generate y01, we should shift the reflected h to the right by 1 unit, and do the production and the summation, you can get the result of y01. It is still 0. Okay, then shift by 2 minutes. Oh, wait a moment. Should 2 minutes, 3 minutes, 4, 5, 7, 6, 7, 8, 9, 10, 11, 12, 30, 14, 15, 8, 30, 40, 15, 16, 17, 18, 19. Yeah, you can see at when n equals 19, actually the output is basically the same as the input. That's because we are using the impulse function as the impulse response of this system. But we can't stop. We can't stop now since there is a. We can't stop now because there is still still a lot of overlapping between these two signals. So we need to continue. We need to continue until there is no overlapping between these two signals. So finally, when n equals 38, we can stop, since if we shift to the right one more unit, there is no overlapping. So it means the n equals 0 is the stop point. So finally, that's why the output single length should be the input length plus the impulse response length minus 1. So this is a question you will answer in the paper. So please remember that the output of convolution, the output length of convolution is the input length plus impulse response length minus 1. And since you can see for this example, if x length is 20 and the h length is also 20, 20 plus 20 is 40 and minus 1 is 30, is 39. And since for this example, our starting index is 0, so the final length is from 0 to 38 is 39. Okay, that's the convolution. Okay. Okay. Next thing I want to say is about the correlation. And since actually correlation is an application of convolution. For example, this is sorry, one moment. This example. Oh, for the autocorrelation, actually, this is autocorrelation of x1. Oh, maybe, yeah. x1 is defined as this way, and the x1 minus n is the reflection of x1 of n. So it's defined as this way. And the autocorrelation actually can define with the convolution in this way. And you can see if we just think about this is our impulse response H, and then it can be written. It can be written in this way. Actually, this example, this example is to show the autocorrelation. Show autocorrelation according to this equation. It k minus n. It's just like this way. I mean, oh, wait a moment. Correlation. Correlation function. To right to the shift, right from right or from left to the shift. Okay, according to this equation, you can see we still use the 3 steps of convolution. And the firstly, we should generate the, sorry, wait a moment. Firstly, we should generate the singular x1 of k minus n. Since actually this means we just shift the x1 singular to the right by n unit. So, and then do the production and do the summation over k. That's we can show this progress by using this figure. If we want to calculate if we want to compute the autocorrelation of x1 of k, we firstly generate the singular x1 k minus n. Actually, since if n equals 0, actually it's x1 of k, so it's the same singulars like this way. If n equals negative, if n equals minus 21, so it means I have shifted this x1 singular to the left by 21 units. So it's this singulars. If n equals 21, then this singular is shift, and the x1 of k is shifted to the right by 21 units. So it's this singulars. So according to this, we just move the n. We just move the n from minus 21 to the 21. We can generate the autocorrelation function of x1. So this is the final results. You can see when n equals 0, we can get the maximum value here. Maximum value means both of singulars are perfectly matched. So since they are perfectly matched, they can when you are doing the production and the summation, you can find the maximum value. So you can use the you can use the autocorrelation function to decide when the signal is start. When the signal starts. So according to this example, we can see when n equals 0, it has the maximum value. So we know that the starting time index is 0. So this is the convolutional application called autocorrelation. For the cross correlation, I think they have the same. They have the same. For the cross correlation, when we have the same. Sorry, how to say that? Oh, for the cross correlation, we just use the same convolution, but it let me wait a moment. Lab 2. Wait. Okay. For the cross correlation, you can see we still use the sorry, this X correlation is the built-in function, which help us find the correlation between two signals. If this Z is replaced by X1, and then the output is the autocorrelation. So what I want to say is that a correlation and cross correlation is just like autocorrelation, and the difference is that we just replace the input signal with different signals. So now I think I have all the I have covered all materials of this class. I will not talk about the part 3, since the part 3 sorry. Oh, wait a moment. Okay. I will not talk about the part 3, since this actually this is your homework task, and I can just give you some hint. Wait a moment. Give you some hint that you will use the autocorrelation function. Oh, you will use the correlation function and find the maximum value to decide which part is yours. So you can get it by using the correlation function. You can use it very smoothly, and I think this is not hard for you. You can finish it very soon. And the next part, I want to show some basic. I want to show some basic basic knowledge of how to use MATLAB to generate signals in MATLAB way, and cover some samples over this lab 2. And sorry for this. Please rejoin my Zoom now, since my Zoom has the time limit. So can you rejoin our Zoom? Okay, okay. Sorry about that. Rejoin. Da, da, da.